Again I welcome you for this lecture on pile foundations. It is in continuation of our last lecture where we have started discussing soil pile system, and continue with that. For the soil pile system we have already talked about the case when the soil modulus is constant with the depth. The second case when the soil modulus is linearly varying with the depth is shown in this figure, and you can see that in this case again the whole system has been discretized in the elements of delta x. So, you have again here this is delta x, another layer. So, what you have continue with this, this is discretized, but now this here this the modulus of subgrade reaction is varying linearly with the depth and it is increasing. So, you could see it is 0 at the here and then continuously increasing. So, what will happen? Suppose I am considering this layer this first layer here to here, which is the thickness of delta x. So, the value here will be the value of this k in this case will be k here will be eta h into delta x, while here the value in the at this level will be k will be eta h into 2 times of delta x. So, with this formulation, and then you want to find the value of spring constant at the middle of this layer, right, and middle of this layer you have the value will be this this value is varying, and what you get here in this case. So, basically total thickness half part of will go on the top and the half part will come it down. So, let us first talk about this layer. At this level what happens, this is a kind of a scenario here. So, you can plot like this and you can see here. So, this is varying. So, here the average value at the middle of this layer is eta h into delta x, and thickness of the layer is delta x. So, as a result the spring constant will be simply middle layer value multiplied by delta x. So, you get eta h delta x square. So, you continue with this 2 eta h, 3 eta h and like that, and minus 2 in then this one, while on the top it is you find the value at the here, then for the top, and the half this is delta x by 2 only, this one, and when you work then you get eta h into delta x square by 8, while on the bottom layer you get this value 4 n minus 5 8 eta h delta x square. So, this was the case when the soil modulus is varying with the depth. Now, what did we do for these two variations? First one is when the soil modulus is constant with the depth, and the second one when the soil modulus is varying with linearly varying the depth. Then we find what is called the natural frequency of the system, and this natural frequency of the system is find out in the form of what is called dimensionless ratio, and this dimensionless ratio is simply said the first natural frequency divided by the properties of the soil pile system. And what property that has been used, simply I can put like this one, that how this FCL1 is defined, where FCL1 first itself, what is the meaning of this? Cl means basically clay. 1 is denoting the first mode of vibration or fundamental mode of vibration, first mode of vibration. So, this FCL1 in this case is defined basically omega n1 divided by k by m, like this, and once you have k by m. So, what has been done, omega n1 divided by k is small k multiplied by r, while m is w by g. So, how this equation have come? So, this equation can be worked out from this, where r is called the relative stiffness factor for the case when the soil modulus is constant with the depth, and you may be aware that this is given by this relation E by k root 1 to power 4. So, this can be found. Once r is known, then we put in this equation, find this constant FCL1. This was the case when the soil modulus is constant with the depth. But if the soil and for this case some chart has been plotted, and this is the chart here. What in this chart, for the different values of maximum depth factor Z max, this frequency factor FCL1 has been plotted here, and there are two cases. One case is when pile top is fixed against rotation, and another case is pile top is free to rotate. So, and you could see that when this value of Z max is more than 4, then it becomes almost constant for both the cases. That means, this value becomes constant, and this value is roughly around 1.2 and this value is around 0.85. So, here in this case you get pile top free to rotate and pile top fixed against rotation. So, according to what is the condition at pile top, you can select either this curve or this curve, and for a given value of Z maximum depth factor Z max, you can find what is called frequency factor FCL1 from this chart. So, in this figure the variation of frequency factor FCL1 with Z max has been plotted, in which Z max is equal to Ls by R, and thus for the given soil with pile characteristics, flexural stiffness EI, soil stiffness in terms of K, sustained vertical load W and Z max, unique frequency factors will exist. So, this has been given from this chart. So, what is done? You find the value of FCL1 from this, and once FCL1 is known, then you can find omega n1 from this equation. So, this we will discuss when we discuss a numerical example. This was the case when the modulus of subgrade reaction is constant with the depth. However, if modulus of subgrade reaction is not constant with the depth and varying linearly with the depth, then the same factor is called FSL1 and FSL1 prime. Here two different cases has been used. One was the case FSL1 because the charts are different. So, the FSL1 is the case when you have this pile top is free to rotate, while the second one the prime is used when the pile top is fixed against the rotation. The definition is same as before, and basically again this can be also simply written as Wn1 divided by K by M, and this is basically what you have Wn1 as Wn1, you should be this divided by K in this case will be eta h T square, while it will be W by G. So, using this relation you can work out and simplify this. T in this case is given by EI over eta h. So, T is given from this relation here, okay, and T is called relative stiffness factor. Here eta is the constant of horizontal subgrade reaction, which we have already discussed in the earlier lectures. Now, for this case the chart is given here, and you could see for these charts the depending on the value of T, there is a basic difference here, that this first of all the charts are different charts, that you have this for the case for when this is constant with the depth and varying with the and then second thing like you have then in this case one is pile top free to rotate, and in the second case pile top is fixed against rotation, and three curves are there. The first curve is when T is 0.75, 1 and 1.5, second curve is for 2 meter and 3 meter, and the same is the case here. So, first of all what we do, we select the value of Z max, we select the curve corresponding to the given value of T and find this factor frequency factor FSL1 or FSL1 prime, whichever is the case applicable. Now, for the continue with the natural frequency of the system, there is a using this figure what we do, we then find the non dimensional displacement with depth factor Z, which is x by T in the first mode of vibration when the pile top is resting against rotation, but free to translate and is embedded in a soil with modulus proportional with the depth. Similarly, the variation of the non dimensional bending moment coefficient with the depth of the pile in the first mode of vibration is shown in another figure. So, what you can see here, so this is the case non dimensional coefficient deflection coefficients, when Z max is 2, then this is linearly decreasing. So, which is basically for ridged pile, and when Z max is more than 5, 10 and 15, then you can see that this is continuously decreasing, and this is the case when what is called the long pile. So, these things issues we have already discussed. One thing you can notice that for all the value of Z max, thus non dimensional deflection coefficient B by 1 is the maximum when this Z is 0, that is 1 here this ratio. So, this is the maximum it is showing that maximum deflection will occur at the pile head, and which is expected. However, when we have the bending moment curves, the second curves are for bending moment, and their bending moment coefficient Bm1 is given here, and the variation with depth is shown here. So, what you have, there are 3 different curves again, one is for Z max equal to 2, 3, 5, 10 and 15, and the last curve, from the last curve you see the maximum value of this this bending moment is the case when this z max x by t equal to you have this x by t equal to 1.3, and for this value of x by t 1.3, the value of BME1 is 0.315, this is the case here. So, this could see this is the value 0.315 from when BME1 this is x by t equal to 1.3, and this is the case when pile top is free for translation as well as rotation. So, this is pile top free to rotate. So, this is the case, and here also first mode of iteration pile top free to rotate, for both the curves are there. Now, continue with this. Let us talk about that how using the whatever the theory we have discussed, how this theory can be used for seismic analysis and design of piles. So, based on the dynamic analysis and the concept of the response spectrum, the following method of analysis and design of piles against earthquake may be used, and for this analysis the following data must be obtained. First, what the data required? First thing is you require soil characteristics and boring logs of the site, because either you require the value of kx or you require eta h. If your modulus of subgradation is constant with the depth, you require kh, otherwise you require the value of eta h, that is linearly varying with that. Then you also require the pile characteristics, size, you also require the value of EI, length and type of pile. Then lateral load deflection of the pile under static condition for estimation of k or eta h is also required. Then continue with this seismic design of piles for what these are the design steps. Estimate the dynamic soil modulus k or eta h based on the principles of discussed earlier. In the absence of elastic data, the values from a static lateral load test may be modified based on engineering judgment. Then next is compute the relative stiffness factor R or T and calculate the maximum depth factor Z max for a pile, and Z max in most of the cases you will get more than 5, but that Z max is basically, you may be aware that Z max is Ls, which is the length of the pile divided by T, or it can be Ls by R. When you consider the first one Ls by T, then in this case it should be greater than 5, while in this case it should be greater than 4. But normally you get more than 5 in all the cases, so that should not be a problem, and because it is a long pile, and then it can qualify for the long pile. For the computed value of the maximum depth factor and the pile end condition, read the frequency factor, that is FCL1 or FSL1. And once this is known, then estimate the dead load on the pile, the mass at the pile top which may be considered vibrating with the piles is only a fraction of this load. So, first of all, what is the total mass, lumped mass at the pile top. Then once that lumped mass pile top is known, that is basically W, capital W. So, using this data, then you can have thus you can estimate using this equation, objective is to get the value of Wn1, and Wn1 can be find out simply FCL1 divided by WGKR. So, same thing we do here also, using in this case also Wn1 is FSL1 or FSL1 prime divided by W by G into 1 over eta Ht square. So, basically, and in these both the cases the value of FCL1 or these values should be read from the charts which we have discussed earlier, and for the charts you require only these charts basically for these charts, read from this chart, and for reading this chart we require either T or R and Z max only, that is it, nothing more is required. And once you read these values from these charts, then we get the value of omega n1 for both soil modulus constant with depth or modulus proportional to depth, whichever the case may be applicable. Then compute the time period, which is Tn1 is 2 pi over omega n1. So, once omega n1 is known, then time period can be computed from this relation, and for this computed time period determine the spectral displacement Sd for assumed damping from figure which is given in next slide. So, computed time period you may have, and that this is the maximum displacement of the pile head. If an oscillogram for a site has been available, then spectral response is determined for this ground motion. For the soil pile system 5 to 10% damping may be assumed as suggested by Prakash. So, what is for determining the value of spectral displacement SD, which charts we use, which is the given in this figure, the left hand side this chart. So, let us analyze this chart. What you have on this x axis, period in second, which is varying from 0.01 to 10 second, while on y axis you have velocity in second, which is from 0.1 to 0. So, what you have is going up to like you have in inch per second up to 100, and then you have here the different damping curves. So, the top one is for 0%, then 0.5, 1%, 2%, 5% and 10%, different for the damping ratios. The curves are given, and for period this is called tripartite graphs. So, what you can plot, let us say for 1 second, you go from here, select the curve, let us say for 5% damping this one, this point, and this point, if I put a horizontal line, then you will get the velocity. If I get an 45 degree on this axis, then you get displacement. If I plot on this axis, then I got acceleration. So, it could be acceleration, it could be displacement, you can find out, or using this chart for given period and given damping ratio, you can find both spectral displacement, spectral velocity and spectral acceleration. So, our objective is to get the spectral displacement SD from this chart, and what is required? The period only is period and damping is required. So, considering let us say 5% damping, and for the period has been already found out from this above step, that value of the period has been known, and then once it is known, then you can calculate. Then once I estimate the maximum bending moment, the pile section can be estimated for the soil modulus constant with the depth, then you can find AME into KR square into SD. And here AME is given in the table here, coefficient AME is given in this. So, coefficient AME depends on the maximum depth factor 2, 3, 5, 15. Normally Z max is more than 515. So, we have this, we need to have this value only, and when pile top is free to rotate, then this is 0.32. However, when it is fixed against rotation, then negative is 0.9 and 0.18 is the positive value. You may be aware that out of negative and positive, the maximum value will govern in the design. So, this will be the value which will be governing in the design for pile fixed against top rotation, and pile top free to rotate, you have only one value here. So, in this case AME is found from this table for the case whichever is applicable, and once AME is known, then we can find the bending moment AME into KR square into SD. SD has been already found in this step, R is already known, K is also known. So, bending moment is found from this relation. So, this was the case when soil modulus is constant with the depth. If soil modulus is varying with the depth, then bending moment is found from this relation BME into eta h t cube into SD, where BME is given from this table, coefficient BME, and in this table you have again maximum depth factor. So, 5 to 15, when the depth factor is 5 to 15, then you have got 0.315, 0.90, 0.28. So, what you get here, the pile fixed at top against rotation, again the maximum value is 0.90 when pile fixed at top against rotation. So, this was the case here also, whether you have this AME as well as BME, the maximum value is 0.90 for this case. So, this is mostly applicable, this value of 0.90. So, for BME this can be considered, and the pile section need to be checked against these moments. So, what we do continue with this seismic design. For the computed maximum ground displacement, the displacement all along the length of the pile may be determined by assuming that the deflected shape in vibration is similar to one under steady conditions. For soil modulus constant with depth or soil modulus linearly varying with depth, the solution of Davison and Gill and Reach and Matlock respectively may be used for two cases. So, if your this soil modulus is constant with the depth, then you use the Davison and Gill solution. If it is linearly varying, then we go Reach and Matlock 1956 solution to find the variation of this. So, basically what is done here, using this dynamic analysis you find the natural frequency will give you a period, using the period you find the spectral displacement. So, up to that point is fine, but how the displacement, this spectral displacement is the maximum displacement of the pile heart. However, how this displacement along the pile depth will vary, then again we use the same theory which we have used for, let us say for the lateral load, that is either Reach and Matlock theory or Davison and Gill theory. So, what is done here, the soil modulus constant with the depth, then you have this P x, once you know that this is k into y x is variation of this displacement along the depth, and that can be find out from this the methods which we have already discussed. This was the case for soil modulus constant with depth, and the second case soil modulus linearly varying with the depth is given by here. So, now this is the last part of this lecture today. Whatever we have discussed in the theory, let us have one numerical example on that. And for this case, you need to understand that what has been given, that a pile which carries a vertical load of 77.6 ton and the base year on that pile cap is 3 ton. If the soil is sandy in character with phi equal to 30 and eta h equal to 1.612 kg per centimeter cube, under dynamic loading determine the maximum displacement of the pile head, maximum bending moment in the pile, soil reaction diagram along the length of the pile. Assuming that EI of the pile is, that is the flexural rigidity is 3.8 into 10 to power 10 kilogram force per into centimeter square, and the diameter of the pile is 30 centimeter, 0.3 meter, length of the pile group is also given 12.2 centimeter. So, then we need to solve for these 3 cases: maximum displacement of the pile head, bending moment of the in the pile, soil reaction diagram. So, continue with this. So, first step is eta h is given to you. Once eta h is known, then EI is also given. So, simply the value of relative stiffness factor T can be find out from this relation, okay, and where you have this 118.7 centimeter. So, ultimately you get 1.187 meter. And in step 3 you get the value of Z max as 10.27. This is the ratio of what you have, this 12.2 divided by 1.187. So, this is the ratio, that means this is being greater than 5, it is a long pile. So, it is not an issue. So, this will be qualifying for the long pile, and the solution which is given by Reach and Matlock can be used for this case also. But before that, let us find the maximum displacement at the pile head. So, for that we do the dynamic analysis. For the dynamic analysis, 2 cases are considered. One case when the pile top is free to rotate, another case when pile top is fixed against rotation. So, and these the charts are given. Because the value of T is 1.187 meter, so we need to use the first curve, that is T equal to 0.75, the first top curve is used. And from this top curve, when the Z max is here, Z max is you find out 10.27. For this value of 10.27, you see that this becomes even constant before that, and you get this value of around 0.65 from this curve. So, 0.65 is coming from the first curve, while the same scenario for the second curve, you have this for T equal to 0.75 to 1.5 meters. So, this curve need to be used, and you get this value 1 from this curve for pile head resting against rotation. Now, the mass of the on that lumped mass is given 70.6 ton, and which will be equal to ton has been converted into this was basically mass. You can say that I am equal to this, you treat like this, W by G, where G is acceleration due to gravity, which is 981 centimeter per second square. So, putting all these numbers, you get this mass from this equation, and once mass is known, then you can find the first natural frequency from this relation, FSL1 divided by W by G 1 eta S T square. Here FSL1 has been already decided 0.65. Now, put the other values, W 70.76 ton, and then you have this is G 981 and T square is given here. So, this is 1.612 G, and this is eta H, and this is the value of T square. So, putting all these numbers, you get the first natural frequency in radian 11.014 radian per second, and for this natural frequency in the radian, you find the this frequency in hertz as dividing by omega n divided by 2 pi, you get 1.753 hertz. So, 1.753. So, the natural frequency of the system when the case pile top is free to rotate is 1.753 hertz, and we continue with this. Once you know the natural frequency, then find the time period, and once time period is known, then you find that time period is 0.570, and using this chart we find the value of this displacement from here. So, what is here? Tn equal to 0.57. So, here is 0.4, here will be 0.5, somewhere here it will be 0.57, and then I continue with this. So, what it cut it here, this is the point where there is intersection, and from this point we need to drop a line on the displacement axis. So, you are dropping it here and you get it, ultimately you end up S d equal to, once I draw this line. So, this you get S d equal to 0.8 inch, this in inch. So, putting this line, so let us say that if I draw a line here along this, so you get around 0.8. So, 0.8 is obtained, that is equal to inch, this is in inch, that is equal to 2 centimeter. So, 2 centimeter is the displacement given, and the maximum displacement of the pile top is 2 centimeter. So, this is the outcome of this analysis, that the pile may undergo deflections with a maximum deflection of 2 centimeter at the top. Then maximum bending moment can be found out. This is the case when pile top is fixed, pile top is free against the rotation. So, for that case BM is 0.315 from the table which we have discussed, eta h has been given, T has been calculated, and this eta h has been divided by 1000. So, to make it in ton, and then you put the number, the spectral displacement is 2, and finally you end up here in maximum bending moment comes out to 1698 ton centimeter. Then what we want to find the variation of the deflection along the depth. The variation is given along the depth is y is equal to a y q z t cube over E I, which is given from, you could see here from this relation. In this relation, this can be written as a y into b, where b is nothing but, in this case naturally the capital B is nothing but q g t cube over E I. Okay. For the soils with modulus increasing linearly with the depth, a y equal to 2.435, therefore, constant in the above equation is b, value b is comes out to be 0.821, and once you know the value of b, we put y x equal to 0.821 into a y. So, your equation is ready, and in this equation when the a y varies with the depth, your y x will be also varying with the depth. So, this computation has been shown in the table, but before that I will like to say one thing here, that soil reaction can also be find out. Here in this equation, this is basically P A is equal to gamma into B into x into 1 plus sin phi divided by 1 minus sin phi, and if you put all the numbers, which is gamma is value is gamma is given, and I can show you here that these numbers are given here. So, the value of gamma is given to you in the question. Gamma is given 1.8, and then 30 centimeter pile, and then 1 plus x, and then 1 plus sin phi equal to 30, and 1 minus sin phi 30. So, ultimately you end up, if you solve this equation, then you end up 0.162 x in kilogram force per centimeter square. So, that means the value of P A, this is what is called the soil reaction, the allowable soil reaction, that is not constant, rather it will be vary with the depth, and the computation, whole computation is given in this table, and you could see in this table that you have the value of x, z and a y, and for these values you put a y in this equation, and then finally deflection y x, and then eta h x, and finally the value of P. However, the value of P A can also be added in this column, and P A is given by 0.162 x, which is in kilogram force per centimeter, and if I put the numbers here, then this will be 0 here, and this will be 16.2, and then you get 32.4, and next value is 48.6, then you have got 64.8 and 81, and then finally 97.2. So, these are the numbers. So, you could see that if you compare the value of P and P A, so naturally both are 0 at the top. However, there is a large difference in the second value, and then Pa keep increasing while your this keep fluctuating. So, you get reduced and then it becomes 0. So, this is the breaking point, breaking points come here. So, here this is, though we are doing the analysis, your pile will get failed, this is not allowable, not allowable. So, that means it require, because allowable pressure is less than the pressure which is coming. So, it require a different design. So, this was the case when pile top is free to rotate, but the second case when pile top is fixed against rotation, then what you need to do, you need to change the value of Fn1, and Fn1 in this case ultimately this because this factor which was coming the FSL1 you got is FSL1 prime was coming 1 instead of 0.65. So, as a result your this Fn1 for this case you will get, instead of 1.753 you get 1 into divided by 0.65 into 1.753. So, you will end up here in 2.697. So, 2.697 will be your Fn1, and as a result your Tn1 you will get Tn1 equal 1 over Fn1, which you will get 0.370 second, and for this value then you find this SD, and this displacement for this case for Tn from the chart comes, spectral displacement comes out to be 1 centimeter, and once this is known then you ultimately find the maximum BME comes for this case. BME you will get is 0.90 from the that is the maximum value for the case, and ultimately you end up in getting the maximum bending moment in this case comes out to be 2426.4 ton. And how this have come? I can give the details for this. This is 0.90 into 1.612, which is the value of gamma, divided by 1000 into 1.87 cube into, then you have 1, SD is 1. So, you end up here this value 2. So, you could see that the value of maximum bending moment is quite increased compared to earlier one. If earlier one you compare, so the value you are get it here maximum bending moment you got is 1698. So, this was the number here, but when you consider the fixed case then this number have increased. So, this was expected. When pile top is free to rotate, then it will be able to carry the less bending moment, but when it is fixed then it will be able to carry the more bending moment. So, this was the case, and we have shown with the numerical examples. Whatever we have considered in this lecture, in the last lecture, particularly for the vertical vibration for this vibration, you can refer to Prakash and Sharma, the book Pile Foundation under Dynamic Loads. So, the first part was, that is vertical vibration, and for the dynamic analysis, and then given in the book by Prakash, where you can have for dynamic analysis. So, you can refer in these books for details if you want to have this one, and some of the papers are also published later on this one. And with this I thank you very much for your patience for these 2 lectures, which was a little longer than this one, and with this we have almost for dynamic analysis we are done for the pile foundations. Thank you very much. Thanks.